So in this session, we talk about identification of a second order underdamped model. Now for this problem, we are given the data set, the step input, and the response of the process. And we are given the relationships between the model characteristics and the model parameters. So what do I mean by the model parameters are these K, the gain, the tau, and the damping coefficient, and also the time delay. Now by model response characteristics, I refer to this time to first peak, which is TP, which is for the response curve we have the time it takes to reach to the first peak. So we have here seen that response oscillates around the final steady value, so it reaches the peaks several times here. Okay, the time to the first peak and its relation to the model parameters are given by this equation pi tau over 1 minus damping coefficient square root of that. Okay, now do remember that when you are looking at the equation, when you are using it, the equations are consistent in terms of unit. Here you see that damping coefficient doesn't have any unit, so this entire term does not have any unit. The pi is a constant, so doesn't have any unit. So the time, the tau as a unit of time, so TP should have a unit of time. Okay, the second relation is given is the overshoot. Okay, overshoot, which is given as the ratio between this A and the final steady value that the response reaches. Okay, so overshoot is the ratio of these two, A over B. Now again, remember that's the ratio, so the unit should be consistent, so they shouldn't have any unit. And you can see here that okay, this is an exponential term, so it doesn't have any unit, and it has got this damping coefficient here without any unit and the square root of 1 minus damping coefficient squared, so it doesn't have any unit for this case. Now the decay ratio is defined as the how fast the signal is decaying, and that's given by this. If for the second peak the value is C, the decay ratio is given by C over A. Okay, the last equation is given P over twice pi tau over square root of 1 minus this damping coefficient squared. Again, this doesn't have any unit, this doesn't have any unit, so the period of oscillation has a unit of time. Okay, so make sure that when you are given the unit or when you use the unit, you look at the relations and make sure that they are consistent in terms of their units. Okay, now take a look at how you can really approach this solution. So we need to find out these four parameters. K equals now we know that from the definition of K, we can directly find K from the ratio between delta Y and delta U. Okay, so for K, we do not need any of these equations, so you can directly find it there. The theta is the time delay, which is the time it takes for the response to start. Okay, so you can also find it from the curve there. Okay, so for K and theta, we don't need any of this equation. Okay, now to find tau and this damping coefficient, we need to use this equation, some of this equation, not all. Now if we look at this equation, this TP and this P, they have both tau and xi. Now if you start with this equation, you really cannot find the values directly, you'll have to use other equation. So why not use this equation where you have only this one parameter, this damping coefficient. So if you use this, so you'll get the damping coefficient directly. Now this two equation, if you look at this, the decay ratio is really nothing but this A square of this term. Okay, so from the overshoot and decay ratio, we can really only get the damping coefficient, we cannot get anything else. So we don't really need to use both of this equation, just one will be enough. Okay, so based on this analysis, we see that okay, you can start with finding the value of k. Okay, so now, let's look at the solution. So step 1, and find k. So what is k? We know that k is nothing but delta output over delta input, meaning how much the output was changed because of the change in the input. Now for this case, we see here. Now you see, before going to that, the time scale here, you can see here that we have here value of 0, meaning it is scaled from 0, so we don't need to change the scale. Here we see that the size of the step is, what is delta u? So delta u is u so we have y, we have delta y, again y infinity minus, we have the final value is 13 here, and the initial value was 10, 3. So you can get directly k equals 2. Okay. Now step 2 would be find theta, that's the time delay. If you look at the response here, so the input is changed at time 0, and we see that there is a little bit time lag here. So you should carefully look at when if you are modeling the process as second order, you should look at the timestamp at which the process start to change. So it's something like here, we can see that the process started to change, and if you look at this, the value may be around, say, 3 or 4. So directly you can get theta equals 4. Okay. The third step, we said the third step, you can use that. Use either of these two equations to get this damping coefficient. So find. Okay. Now for doing that, if you look at the relation here, we have the overshoot equals e to the power negative pi zeta over 1 minus xi square, its square root. Okay. So for this case, we need to find what is the overshoot. Now from the curve here, you can figure out that what is the value of a. So a is nothing but this. So a you can look at, to find this, to find a first, a equals, say here it's 14.8 around, minus this final steady value, which is 13, it's 1.8. So b equals, you know that b equals 13 minus 10, 3. So we get overshoot equals 0.6. Okay. Now the relation between overshoot and the decay ratio, if you reformulate this equation, you will get e to the power overshoot. From here you can get negative pi xi over 1 minus xi square equals ln of overshoot. Okay. If you take a square on both sides, you will end up getting pi squared So from here, you will get Now if you simply plug in this value here, it will be so if plug in these values, it will give a value of 0.0258. Okay. So from here, if you simply take this, so you will get 0 equal 0.16. Now we have found the value of this damping coefficient. The step 4 will be find. The last step is to find tau. So tau is related to two equations, Tp and the P. And from here in this equation, we can find out what is the value of this period of oscillation here. The period of oscillation, it's, if we take this time, to find tau, we'll need P. So the P here is sometime around 185 minus this time around 75. So this gives us some 110. Okay. And now directly you get this from this relation, you get tau equals twice pi. If you simply plug in this value, you will end up getting a tau to be around 17.3. Okay. So now we have seen we got the value of K, which is 2. We got the value of theta, which is 4. We get the value of tau, which is 0.16. We got the value of this damping coefficient, which is 0.16, and the value of tau, which is 17.3. Okay. So if you finally, you can write down the equation to be ys 2 over 17.3 squared is squared plus 2 times for S. Okay. So that's your final result for this case. That's the final model you get.